So I'm happy to introduce Dakotah Lambert, who is a third-year PhD student and amazingly is defending his dissertation in about 2 weeks on April 8th. And so you're welcome to come back here on April 8th. The defense is public. It's going to be in this room. I don't know what the time is, maybe 10 o'clock.
I think it's 11.
Maybe it's 11 o'clock in the morning on April 8th. Today he'll be talking about part of his dissertation work, the structure of distinction, classifying function complexity. Thank you, Dakotah.
Thank you, Jeff. Great. So the first question that I'm going to discuss is just what is phonology, because that's basically the theme of this, is like what are the things that happen in phonology. So phonology is the rules that govern systematic variation in pronunciation, and they actually come in two forms. There's constraints and there's functions. So a thing that we might call word final devoicing that happens in German and some other languages could be expressed as a constraint, just as you can't end on something voiced. So you can't end on like a D or a B, but you could end on a T or a P. This doesn't actually tell us how to fix the problem if it occurs. It just tells us there is one. The function, on the other hand, tells us like what we actually need to do if we encounter a form that the language doesn't want to have. So in this case, the function is you devoice word final consonants. You turn your D into a T, you turn your B into a P. Another thing that happens is high tone plateauing. That's in Luganda and some others. The constraint form there is you can't have a high and then a low and then a high in that order in any word. The function in this case is you can turn lows into highs whenever there's a high on both sides. There's other ways of solving the problem. For example, after an L, you could just change all of your highs to lows. So there's multiple ways of solving the same problems. So we want to know what kinds of patterns actually happen in the wild. We also want to know what we need to be able to do in order to learn them. And moreover, how do we do this learning when presented only with sparse data? And these questions are actually related. So learning requires two things. You need a space in which to search. That's basically where all of the possible patterns are going to lie. And then you need to know how to generalize from data to the patterns in that space. And if you have every constraint in the world or every function in the world, and you know what all of their complexities are, well, that tells you what's sufficient to do the learning. It can tell you what's necessary in a sense when restricted to the set of classes you're considering. Something is necessary if it's attested. But there might be other ways to factor out a problem or to state the constraint. So truly, this is only necessary if no other options exist. But this does get us at least a step toward finding necessary and sufficient conditions for learning. And so my contributions here are a unification of the schemes for classifying sets and functions, and setting a lower upper bound than was previously thought on the complexity of phonological patterns. I pressed the button and it didn't go. So to do this, we're going to use algebra. Just a little bit of it though, nothing too fancy. So we're going to start off with some terminology. So what's a semigroup? Semigroup is a set in an operation. The set's closed under the operation, so you take any two things, put them together, you get a thing that's still in the set. And it's associative so that you can write expressions without needing parentheses. That's it. There's nothing else to it. A monoid is a semigroup where you have an identity, call it 1. 1 times A is the same as A times 1 is just A. A free structure is when those are the only properties that hold. And this really lets us talk about words as algebraic objects, because you can just say the free structure is all the finite sequences under concatenation. ABA is not the same as BAB. So that's not one of the rules that we have. So all the words are inherently distinct. So what is a language? It's just a set of words. It's possibly infinite set of words. We don't necessarily want to deal with infinitely many things. So we talk about how things behave. There's a couple of different ways to think about how things are behaving. There's the Nerode equivalence, which is a one-sided deal. Basically, if you have two words A and B, do they act the same way for any suffix you can put on them? So AX is in L, if and only if BX is in L, it means they act the same under suffixation. They're Nerode equivalent. There's also Myhill equivalence, which is a two-sided generalization of this. A is Myhill equivalent to B if for all prefixes and suffixes, wrapping those around, it behaves the same. And we just write things in brackets to say the equivalence class under the relation. Here I'm just using tilde as a generic relation. And so we can look at some examples. I'm annoyed by the Zoom bar being over my titles. This is that's even worse.
And also, I think Dakotah told me earlier that Dakotah told me earlier also that if you have questions, you can ask questions during the talk. I think people who are joining virtually and people in the room, I think the best thing to do is just to start talking and interrupt if you have
Right,
questions.
yes.
Okay?
Sorry, I forgot to mention that. Where is that? Thank you. Okay, so an example, asymmetric harmony. You can't have a B-type thing anywhere in a word after an A-type thing. This happens in Sarsi. See Hines 2010 for an actual concrete example. The Nerode relation induces three classes on this. You've got the A-B class, just things that contain an A-type thing, and then somewhere later a B-type thing. There's the A class, which is things that contain an A-type thing, but not in AB. And the class of the identity is everything else. And here's some things that contain A, but not A and then later B. A and BA, both of those are in the A class. But AA stays in the A class, while BA goes to a different class. So you can't just say the class of A times the class of A. It's not a well-defined operation. So maybe the Nerode equivalence isn't what we want. It doesn't really let us compactify things in the way that we want to. Spacebar died. So let's try the Myhill relation. This gives us more classes. There's 5 of them this time. There's AB, again, is the things that contain an A and then a B. And now there's BA also. That's things that contain a BA, but not an AB. A is things that contain A but not B. B is things that contain B but not A. And 1 is everything else. And this, we can just throw some examples out here. And it does look to be compatible with concatenation. A-type things followed by A-type things are still A-type things, etc. And we can actually show mathematically that anytime we use this Myhill relation, we always get this compatibility. So if A is Myhill related to B, you can take any prefix and suffix, they'll behave the same. Same for X and Y. So we can just reassociate and swap things and show that UAX V is equivalent to UBY V. And there we go. AX, BY has to be equivalent to A and B, and X and Y are. That means we're compatible with concatenation, and we can impose a structure on these equivalence classes. We take our infinitely many strings and compact them down into, well, in this previous case, just 5 examples. Nice. So here's another example. Restrictions on endings. This is our German word final devoicing example, where the constraint is you can't end on a Y-type thing. Here, the Myhill equivalence, which is the only one we're going to be considering further, induces 3 classes. One is only the empty sequence. It's the only thing in that class. Y is things that end on a Y-type thing, and X is just everything else. And we can put them together with our induced structure and get this multiplication table. 1 times anything is the thing, anything times 1, still the thing. That's how identities operate. X squared is X, Y squared is Y, but also XY is Y and YX is X. So we can take this table, our multiplication table, and we can talk about what's known as the Green's relations on it. They were proposed by a guy named Green. Things are L related if their columns have the same things in them. And so here I've boxed the columns in this like orangish color. They're all distinct. Nothing is L related here. Things are R related if the rows have the same things in them. There's only 2 R classes. X and Y are R related because both of their rows contain X, Y, and nothing else. But one has 1 X and Y. So that's distinct. These are H related if they're both L and R related. So no 2 disjoint things are H related here. And they're D related if the R class of one and the L class of the other have something in common. So here, X and Y, they are both R and D related. If you're R related, you have to be D. If you're L, you have to be D. But also, more things can be D. And there's also J, which people talk about. It's the same as D, so we don't really have to care about it, at least on finite things. And so we can take this picture here, and we can turn it into the thing on the right, which is what's known as an egg box diagram. The name comes from the 60s. Basically, every block is a D class, and the things, it's partitioned into rows that are R classes, columns that are L classes. So the X and Y, they're R related, they're in the same row. And they're put in this order. The order doesn't particularly matter, but essentially if you put 2 things together, you can never go up, you can always go down. So here we have 2 blocks, the 1 block and the XY block, and they're arranged in this way. And so we can actually put our structures in a comparison using these. So we take our first example, the asymmetric harmony. Here's its complete multiplication table. And if we look at the rows and the columns, we see there are actually 5 distinct classes. Each element gets its own box. Whereas on right, the word final devoicing example, we have two things sharing a box. That's okay. So what does this mean? Well, we get a hierarchy of complexity classes. If no two things are H equivalent, they're called H trivial. If no two things are in the same block, then you're J trivial. If no two things are in the same block, you definitely can't have two things being H equivalent. So basically, each one of these classes contains fewer things than what's above it. We have that no A, B are asymmetric harmony. It's properly J trivial. There's no two things sharing a block. But can't end on Y. You do have things sharing a block, but nothing shares a column. So that's L trivial, which means it's not J trivial.
But Carter, you're saying that the scarcity example is simpler than the way that this on the grid structures than the can't end on a Y.
Yeah, that is exactly what I'm saying. And we'll see as the talk goes on that this isn't the only way to look at things. And in fact, we can look at some smaller induced structures and show that, in fact, the can't end on a Y thing gets to be much simpler, whereas this doesn't really simplify much at all.
I mean, you think the number of classes like a modular relation is to do with the complexity?
I wouldn't think so. It could, but so there's definitely things where the number of equivalence classes can be really small, but the pattern itself can be really complex. For example, take even A. That's your stereotypical, purely regular pattern that can't be done without that power. There are two elements. There's the identity, there's A, and they share a single cell in your egg box. Yes, repeating the question. So Jeff had asked if the number of MyHill classes has anything to do with complexity. Sorry, I forgot the microphones are not in the room anymore. Okay, so, right, the smaller structures, local subsemigroups. So we have our free monoid over sigma, that is all of our words. We have the free monoid quotiented by the MyHill relation. This is our equivalence classes. There's also the free semigroup, which is what we get if we don't include the identity to begin with. And so if we have our free semigroup, as we've excluded the identity, we can look at what's called the local subsemigroup of something, which is basically where we restrict ourselves to, so if we have an element A, we want to look at only the things that begin and end with that thing A. And an element E, I'm just going to put this here, is idempotent if and only if it squares to itself. Essentially, these are things that can be freely duplicated without changing how the word acts. And so we want to consider local subsemigroups induced by idempotence. Why? Because the local subsemigroup there happens to give us a monoid again, which we have a classifier for. And so let's look at our asymmetric harmony again. Remove 1, but C, if our alphabet was big enough to contain C, it acts the same as the identity did. So we now have our 5 elements again, except the identity has been renamed to C. What's idempotent is everything except BA. So we look at the idempotence, and then how to find our local subsemigroup. There's a nice, easy way to do it. First, we take our row. So the row of C is everything. And then we multiply each of those things again by our element E. And because C is our identity, of course, gives us the same thing. But something perhaps more interesting is the case of B, where the B row contains B, BA, and AB. Then if we multiply each of those things by B, well, B times B is B. BA times B is the same as AB times B, it's just AB. So doing the extra multiplication actually matters. So now we have 4 local subsemigroups induced by idempotents, and we can classify those accordingly. So we take our small little hierarchy again, and we just put things on there. Now, what is J1 class that I conveniently glossed over before? It is J, where further everything is idempotent. And we mark the idempotents by a star in these diagrams just so that it's clear where they live. So we take the lowest thing containing all of them, and that's the complexity of our system. Here, well, our identity was in there, so we keep the whole main structure, which is still a J. But if we look at our restricted endings, we remove the identity here, nothing brought us back to that, so it stays gone. So now we only have 2 elements, both of which are idempotent, and each of them has as its local subsemigroup only itself. So we put those local subsemigroups in our system, and they're as low as you can go. Jeff, does this get back to your question?
Well, it does, because now you're saying that if you look at the, and I think what you're saying is if you look at the most complex local sub, if you equate the complexity of the pattern with the most complex class of the local subsidy groups, then you get a different result here where the voicing would be simpler than the Sarsi pattern.
Precisely. If you equate the complexity with the lowest thing containing all your local subsemigroups, then the p-voicing is simpler than the Sarsi.
Right. You can describe it as the lowest thing containing all the other local subsidy groups, but it's also the most complex. When you classify the local subsidy groups, it's the most complex one. It's going to be the
Well, sure, but if you had something in L and something in R, you got to bump to H.
Then you got to bump to H. Okay.
Yeah. So we put these hierarchies together, and oh no, suddenly it's bigger. It's going to get worse. So basically, we have our main hierarchy, and then we have the local version of it. And so we show that the asymmetric harmony, it's either J-trivial or it's locally J-trivial. The locally doesn't really change anything. But the can't end on Y thing, that's L-trivial, which is kind of high up there. Or it's just locally 1, like as simple as you can possibly get. So looking at these things in different ways gives us a different view of their relative complexity. Another thing that we can do is we can restrict what we're looking at to only the symbols that are salient, symbols that actually change things in some way, that aren't acting as the identity. And that's exactly what we've defined here. So tau, it's not a T, it's a tau, is the set of all symbols that are in sigma that aren't equivalent to the identity. And so if we look at tau plus over the Myhill relation, that gives us even another layer of looking at things differently. For asymmetric harmony, C was acting as the identity, so it's not in tau. And once we remove that, we're no longer in J, we're in J1, which is actually simpler. So we can put this tier hierarchy on there. And while we didn't get to drop this asymmetric harmony as far as the can't end on Y, it still did lower itself some a little bit. Also, locally 1, I said it's as simple as we can get. It's not. So we were looking at things that begin and end with our idempotent. But we could also say things that just end with it, that's D. Things that just begin with it, that's K. Or things that just contain it, that's F. The names have meaning. D, definite. F, finite. K, we forget about. Okay, reverse doesn't start with K. It's not so informative there. But so if you're only a single element, all these are kind of the same. So it doesn't matter. If you're in 1, you're in F. So can't end on Y. It's actually in D. It's not in K or F. So we get this even simpler characterization of this word final devoicing constraint. We've moved it down from L1 to D, and from TL1 to TD, of course. But why? Why are we doing this? What do these mean? Well, like I said earlier, we're constraining our search space. So trivial is a proper subclass of the J1 space, which proper subclass of the J space, et cetera, et cetera. And so where the attested patterns show up tells us the kinds of things that we need to be able to do. Now, which hierarchy we're on, that could help or hurt. Like we show that how you classify things can't end on Y can either be really high or really low. So you want to choose like the best, easiest one. But what do the classes actually mean? So let's look at the J1 example. With a bit of work, doing some algebra, you can show that this has 2 properties. It's everything is idempotent. So x equals x for all x. And everything commutes. It's xy equals yx. Commutativity means that we can sort our strings. And they behave the same way. So ABA behaves the same as AAB. Idempotency means the duplicate symbols collapse, so AAB behaves the same as just AB. And in effect, this means that strings have to be treated the same if they contain exactly the same set of symbols. And that's exactly what J1 means. I'm not going to go through the rest of the classes, but you can see how this can give us a learning algorithm for the class. For J1, you just say, what are the sets that I see? If it has such a set, it's a good word. If it doesn't, it's not. And one last language example before I move on to functions. It's going to be symmetric harmony. We've already discussed asymmetric harmony. Well, the symmetric one is you can't have both an A-type thing and a B-type thing in the same word. This shows up in Samala. See the same Heinz resource from earlier. Here there's 4 MyHill classes. Got AB, which contains both. Got A, which has A but not B. B, which has B but not A. One is everything else. And we put our multiplication table here, and hey, that's both idempotent and commutative. It's in J1. So everything squares to itself. Everything commutes. We're in this nice simple class. It's learnable by gathering sets of attested symbols. Now we get to move on and do the actual fun new stuff. It's generalizing this from languages to functions. So we have a notion of what it means to behave the same way in a language is just to both be in or both be out of the language. Neurode is look at the suffixation. MyHill is look at the circumfixation. And so we generalize these 2 functions by saying, well, Neurode corresponds to what has traditionally been called the tails function. which I define precisely below. Essentially, it's saying, given a string A, for all possible suffixes V, what contribution does that suffix add to the output? And we can generalize this the same way that we did the Nerode operation. It's by saying, let's think about prefixes too. So we take our tails function and say, well, we don't want just Vx. We want to say the prefix U, the suffix V, what contribution does that give? And this gives us a way to take these same algebraic principles and apply them not just to string constraints, but to string transformations. So here's a function, intervocalic voicing. So if our alphabet is oversimplified to contain only voiced things, voiceless things, and vowels, D, T, and V, we could say that this function changes T into D when it comes between two vowels. And you can generate the classes from this. There's 5 of them. It's the identity, T-type things, D-type things, V-type things, and a V-type thing followed by a T-type thing. Immediately. They multiply out like this. The idempotents are highlighted. And I've drawn the identity off in the corner to show that in the semi-group, it doesn't appear. So we get this kind of egg box diagram where we have nothing being L related, 3 things being R related. And we can see just by looking at the multiplication table, it's in D. That implies it's in L. But it's not in J because we have things sharing a box. It's not in R because we have things sharing a row. So that's how we can just at a glance classify the thing. And here's how we actually found what those elements were. This is a different function, but it's the same process. So this is an iterative nasal spreading function. And if you're given a minimal canonical finite state transducer for an operation, you can figure out what the Myhill classes are by saying, okay, for each string, for each state, where does it take you? The identity function is always going to be mapped 1 to 1, 2 to 2, on and on until you're out of states. We're out of states at 2. But here, if we see an n, well, if we're in state 1, that maps us to state 2. If we're in state 2, it keeps us in state 2. So the order of the map here is the left is state 1, the right is state 2. So if we're in T, everything maps to 1. And we see that anything else is going to be equivalent to one of those. After we've exhausted our length 2 strings, we don't have to go further. So we see there's 3 classes. And I didn't draw the multiplication table here, just gave us our diagram. It's got the identity up top. It's got 2 things sharing a class. It looks just like can't end on Y, except the identity is reachable. There is a thing that occupies that slot. So instead of just being D, it's tier-based D, it's TD. It's not even locally R trivial. So we have to get into the tier-based realm for it to be simple. We can also do our asymmetric harmony as a process. Here, we say, after we've seen an A, change all the B-type things into A-type things. Here, B and V, there's self-loops everywhere. That means they're acting as the identity. A is a distinct element because it's not doing the same thing. But AA equals A. If you're in state 1, you see AA, you go to state 2. If you're in state 2, you always stay in state 2. So it's not a whole lot of fanciness you can do there. Here's our diagram. It's got 2 elements, identity up top, A down at the bottom. It's in J1. And it's tier-based finite, but it's not locally one. And for completeness, symmetric harmony. Here, I've just got 3 maps. We have the identity map, which contains 1, contains vowels, these. There's another map, which maps state 1 to 2, 2 to 2, and 3 to 3. That's basically things that started with an A-type thing, or some number of these and then an A-type thing. Then there's the other map, which maps 1 to 3, 2 to 2, and 3 to 3. That's things that started with some number of B's and then a B-type thing. This gives us 2 boxes. There's the identity up top, and then A and B sharing a column below. So it's not L-trivial, it's not even locally L-trivial because the identity is still in there. But it's tier-based decay. Should have put a nice summary here before moving on to the fancier functions.
I have a question for you.
Yeah,
Can you go back to where you said that the asymmetric harmony is pure and finite?
I can.
So what is the finite set of strings and what's the tier?
The tier, the salient symbols, the salient symbol is A. And essentially what the pattern is, it corresponds to the string language empty. Because once you see an A, you know what you're doing for the rest of the universe. You got 2 states. There's the initial state, there's the A state. And if you want to assign acceptance to those, make the initial state accepting, and then it's finite.
So the finite set of strings is just A.
The finite set of strings is empty set.
It's just the empty set.
You can also make it cofinite by making the A state accepting instead of the initial state.
Well, here they're both set.
Here they're both accepting, but I'm saying if you wanted to make a string constraint with the same shape, that's what it would be. Because that's what these are named on, is what they mean for a constraint.
Right. So I'm just, yeah. Okay.
So the word finite doesn't really mean what you want it to in function land.
Right. So I'm trying to understand what it means in function type.
Yeah, it means it has the same shape as
What's the text for the second one?
that's this. Okay, so maybe sound works again. I legitimately cannot tell. Sound back, yes. Okay, so back to your question. Finite means you're acyclic except for one state, which is your 0.
Right. Okay.
Okay. Where were we? forgot that up is actually up now. Okay, so yeah, finite just means acyclic except for your 0, and that's your only cycle. You good?
Yeah, I think so.
Cool.
Yeah.
So non-deterministic functions with string constraints, they're all the same. You can determinize anything. With functions, that's not necessarily the case. And so we can have high tone plateauing. That's a thing that I mentioned earlier. You can't do that with a deterministic one-way function. So we have this machine here that if you're in state 1, H can map you to 2 or to 3. And so we just put sets in there. And basically the identity function maps 1 to the set 1, 2 to the set 2, 3 to the set 3. Kind of a lift. And L is behaving like an identity. It's a self loop everywhere. But H maps 1 to 2 or 3, 2 to 2 or 3, and H to nowhere. So we can expand out until we run out of new maps. We've run out of new maps. All the strings are in there. We get 2 classes, the identity, which contains L, and the other one. So because the identity is in there, we're not locally K, just K. We're tier-based K. And we're also J1 because everything has its own block, everything's idempotent.
To kind of point on, what does non-deterministic mean in the real world example? Is the high tone plateauing there just random?
So it doesn't mean that it's random. It means that you need to consider multiple options at some point in the string. And so here, as you process a string, if we wanted to run through an example, consider the string HLH. So the H will map us to states 2 and 3. The L will become an H in the state 2. So you'll have HH as your prefix there. It'll stay an L in state 3, so you have HL as your prefix there. Then you see your H again. The H falls off of 3. That's a crash. So that HL prefix is no longer under consideration. But the other one, the HH prefix, it splits into 2 states. Also, as the 2 can map to 2 or to 3. So we have 2 different HHH computations right now. We've stopped. We've reached the end of the string. See that the one in state 2 is not accepting, so that one goes away. We're left with only one option, HHH ending in state 3. And in this particular example, there's never a point where you end up with more than one option at the end. If it were a different function, you could end up with more than one option at the end, and maybe that would be random more or less. But in this case, it's unambiguous, but you still have to consider multiple things while you're doing it.
So it's trying to create a simpler example because I can't pretend I completely understood that. I think that, so is it basically that you sort of have to see the whole string before you can figure out if it fits, and you have to see more than just a little bit before you say.
Mm-hmm. That is the main thing that gives non-deterministic functions more power over deterministic ones, and why it's actually cool that on acceptors they can be merged. Jeff was about to say something.
I was thinking about it, but I don't think it's gonna happen.
Okay. So then we can go even more into you have to see the whole thing world and look at what's called a two-way machine. And I don't really want to get too deeply into these because they're weird and I don't like them. Which is why my first point on here is for a two-way thing, there is no normal form. That's also the case for the non-deterministic machines.
Although you don't like them, you might say why it's important in linguistics.
perspective that we consider.
Absolutely, and that's what this example is. So you can witness upper bounds. You can't prove a lower bound because you don't have a form that you can say this is the best we can do. But so this example here is total reduplication, which is you say a word and then you say it again. What the symbols here mean in state one, the loop is anything you see, you output the same thing and go right. Until you see the end of string boundary, which is the fish that you see between 1 and 2. At that point, you output nothing, your identity, and you move back left. When you're in state 2, you've got a loop where you're seeing things, outputting nothing, and going left until you see the start of word boundary, which is the fish you see between 2 and 3. You go back to the right, do it again until you run out of string, and then you stop. That's the two-way machine for total reduplication. You can't do that with a one-way machine at all. And if you want to characterize these algebraically, the behaviors get kind of weird. There's 4 of them now. You got to know what happens if you start on the left edge and you leave out the left edge. Start on the left edge and leave out the right edge. And the same thing starting on the right. And if we do that for this example, for the total reduplication, we see that it's actually trivial. There's only one class. So if you're willing to give yourself this kind of power, total reduplication is as simple as you can get. Which contrasts with traditional thought where people are like, oh, partial reduplication is easier than total reduplication. It's actually reversed. Okay. So conclusions. Because you can do it with a one-way thing. It's order preserving. So essentially what I've done here is I've said we can look at sets, that's constraints, and functions, that's processes, both the same way through this algebraic lens. And doing so provides a nice low upper bound on complexity. Everything that I can think of, every pattern that I've touched is at most tier-based locally J1, which, you know what J1 is, locally means you have blocks instead of symbols, and tier-based is on a tier. So for those who know traditional names for these things, it's locally testable on a tier. And I've written software that does these things. The language toolkit is where all the classifiers live, and that's on the Haskell package thing website. And
So more about what your software does.
a little bit more about what the software does. It does everything. It does everything under the sun. No, that's too bold of a claim. It lets you construct languages from constraints, lets you classify them, it lets you learn them from positive data, assuming you're trying to learn one of the classes that it knows how to learn. One of them that I haven't been too lazy to code up. What else does it do? It does everything. It draws the egg boxes. That's where I got all the examples from. And there's the other repository here, transducers, that basically turns functions into something that the LTK can understand and classify. The next slide is refs. So open for questions. I can see the chat over here for the people on Zoom. The dash lines, they're the same as the other lines, but I didn't want them to be bold and in the way. So it's still
tier-based NCK is a subset of R.
Yeah. So it's a different kind of generalization that gets you that inclusion, but it's still inclusion.
I think again, it's a layperson chemist in this context, but what's the gap between this theoretical understanding of structure and the real world?
Real world languages are evil and noisy.
But you can look at subsets of language and not be excluded.
Could you repeat the question?
See, if you look at a subset of a noisy evil language, would you find a nice clean theoretical one there in there somewhere? Or?
Oh, absolutely. If you just ignore all of the stuff that's weird, then you get something that's nice and clean.
Is there an example of a language that is more clean than others? I mean, English, I realize is a mess. Is Japanese a nice example?
I think like the problem with natural language is that you have a whole lot of things going on at the same time. And in terms of constraints, it's really easy to decompose them and look at them compositionally. But in terms of functions, composition breaks algebra. Your complexity isn't maintained under that. So you really need to find a nice way to do a decomposition for it to make sense in that context. But for a lot of the examples that we've looked at, we can say this constraint holds on all words except for maybe loan words. And so for the constraint-based stuff, it's totally nice.
But I'm a theoretical chemist. But most chemists are experimental, and it's a complicated relationship, I would say. So what's the role of a theoretician in the space of language?
It's the role of a theoretician in the space of language.
Is what?
I was repeating the question.
Okay.
I believe that knowing these things can help us to learn things, machinery-wise, or even to understand what's going on in the head-wise. Whether that actually holds true or not, I don't know. I'd like to believe it.
Keep Thomas's class right now. This totally helps us.
I work on the compositional stuff.
Mhm.
So you mentioned in your answer to Robert that a lot of things happen in a real evil language at the same time. And so in like phonology, we do functions or processes. The traditional view in phonology is that one applies after the other. So as you said, it's going to be measured by composition. And so is this TLJ1 class closed under composition?
TLJ1 is absolutely not closed under composition.
Right. So if we were interested in the complexity of the whole phonology of the whole language, so it seems like here the results are for specific processes.
Right. So here the results are for specific processes, and one can say that they hold in general if one is allowed to have distinct maps that really do serially transduce something. So, if you want to say that the head contains 20 TLJ things in a row, each one of those things only needs to be TLJ.
Right.
Whereas if you want to say, no, the head contains one map that's just do everything, you lose that.
So what does it go up to? Like what's the smallest class that includes TLJ1 that's closed under composition?
Pretty sure the smallest class that includes TLJ1 closed under composition is going to be, well, I didn't actually draw the line here, but I think it's H.
What's H?
I think it's H. I
You
didn't
don't
draw the line.
have a dashed line from H to TLJ1.
I got tired of drawing the lines, especially because H is actually above everything else except for LH and TLH.
Right.
Remind us, what does the top correspond to in the traditional classification?
So H is star free.
To start.
Yeah. Okay.
I haven't drawn regular.
I sort of want to ask a similar question to Jeff, maybe a slightly different way.
Okay.
If I were to pick a language and just, through blood, sweat, and tears, write an FSA, or sorry, an FST, for what I think the process, I just like make it work, can't do it on, and then do the algebraic analysis. Is it the case that it might not end up with TLJ1?
So if you were to take an arbitrary language and just try to do it all at once, you're probably not going to be in TLJ1. But if you can decompose it into things, each of those individual things is probably going to be there.
So you think that not just are we not able to mathematically compose it something, even if I, just as a human were to play around with it manually, I might not be able to get everything.
So if you break it apart, I think everything you break it apart into should be there. That is my hypothesis. But if you want to try to do everything as a single pattern, you're not going to be able to.
I
think that's just composition is weird. There's a hand over here. Owen is still around. He may have left. I think I lost Owen. I think it's too late. Jeff?
Let's ask the question another way, which is like one of these examples, like the high tone plateauing or something.
Right.
Is it possible that we can think of that not as a singular process, but as the result of a composition of multiple processes?
Sure. You can actually do high tone plateauing as a composition of multiple processes, but they don't get any simpler. They're still both TK.
Now, do we know that that's true? Is that true for any of the ways we decompose it, or just the one that we thought of?
That's just for the ones we've thought of.
I mean, the other side of it, the other question that raises is, can you get a stronger hypothesis? If we allow ourselves composition, then it seems like we can, how far can we go and simplify things?
Well, I think one has to consider the ramifications of allowing composition.
Well, I agree with that, but
So, I mean, we're not going to get everything as trivial, but we might fall down to, I don't know, TL1. It seems unlikely, but it could potentially happen. A problem with that approach is that every time you try to break something down, you end up having to say, I have another machine. Phone's down. Does anybody else in the Zoom world have questions? Anybody else in the room?
So there were questions on Zoom or not?
Well, I have asked. Somebody unmuted.
Well, I was just gonna clap.
Well, thank you.
Thanks.